Hi, Dr. Cook here, and today we're going to be talking about the flat fire trajectory. Okay, this is a flat fire point mass trajectory. All right, now this starts with our vacuum point mass trajectory. Now we're going to introduce some drag effects. So we're no longer in a vacuum. We've got some drag going on, but we're still dealing with a point mass. All right, so the assumptions that we have a point mass, which means we can neglect all those body effects of orientation, things like that. That we're flat fire, okay? So this works good if you think about a tank or a rifleman, shooting directly at a target. This is not for artillery or mortars. We have launch angles less than about 5 degrees, okay? That would kind of be with a max where we want to start, not using this model anymore. This is an inertial reference frame, which means we can neglect Coriolis effects. All right, we can also neglect yaw, and we're going to neglect Magnus forces. All right, which all of this then is a low altitude assumption. All right, we're flat fire. We're going to say we're low altitude, near sea level, and we're not dealing with massive changes in air pressures. All right. So the only things that are acting on our projectile is drag and gravity. All right, that's it. So I just want to give a graph. This is going to be a graph of the coefficient of drag versus Mach number. And if you were to, take that out to high Mach numbers and graph it out, you get a curve that looks something like this. All right. So that's how our drag will change based on how fast our projectile is moving. It's kind of a complex curve. We generally just have to get these from empirical data, but they all end up looking like this. All right, and you can see that huge change that happens there around Mach 1 that led to a belief in some form of sound barrier. All right. Now, if we look at this, you'll notice prior to Mach 1, we pretty much have a constant coefficient of drag up until we get to that big spike that happens. All right. And if we go out past about Mach 5, things level off, and we have that also. We see that too. All right, so these are the region that we're going to call case 1. All right, this is case 1 of how we deal with drag. For these, we're dealing with anything that's Mach lower than 1 or greater than 5. That's where we're going to put our boundaries. So everything in the subsonic regime or the hypersonic regime. And we're going to have a coefficient of drag that's some kind of constant. All right, that's our model. That it's some kind of constant. We'll call it a K1. All right. Now, if we look at this graph a little bit closer to how it kind of lays out, we can get a case 2 because there's an inflection point here somewhere around Mach 2.5. All right. So from Mach 2.5 up to Mach 5, we're going to call that our case 2. All right, that is our high supersonic regime. All right, and if we draw a line there, all right, we kind of get this somewhat linear relationship going on with how the coefficient of drag changes with Mach. It's not a constant anymore, but we can kind of fit a little bit of a model to it and say that our coefficient of drag is equal to some constant divided by the Mach number. All right, and so in our case 2 region there, from 2.5 to 5.0, we're going to use K2 divided by Mach. All right, which leaves us with a case 3 in this other regime from Mach 1 to Mach 2.5. All right, this is our low supersonic regime. And if we fit a little bit of a line there, you can see that we're not going to have any kind of linear relationship. There's definitely a curve that we have to account for in there, right? And we're going to kind of model that as some kind of constant divided by the square root of our Mach number. All right, so that is our model in case 3. All right, so how do we deal with these things? All right, each one of these cases has a different set of equations that go along with it that come out of that, all right? So a reminder that in case 1, we have a coefficient of drag that is some kind of constant, all right? We're using this capital K sub 1 as a coefficient of drag. Now from that, we get this parameter that is a lowercase k, so we got to keep our uppercase and lowercase k's straight here, all right? Taking into effect for any particular projectile what is its mass, what is the air density that we're dealing with, and what is the reference area for that projectile, all right? Equation 9.70. All right, from that, we can get a velocity in the x direction at any given point that is equal to our initial velocity times e raised to the negative small k1 times our x position downrange. All right, so if we want to know what a location is downrange, we can look at that velocity with 9.71. Now, if we want to understand something about time and how time fits in here, how long is it taking us to get to these points? All right, we have equation 9.73. All right, again, bringing in our parameter, lowercase k1. All right, and then we have an equation that will get us to our angle. So this is our launch angle there, all right, being used along with our velocity and our position downrange to get us a fall angle. All right, what angle is the projectile sitting at on its trajectory as it goes downrange? All right, or the angle of the trajectory as it goes downrange. And then we get a y position. What is our altitude above the baseline? All right, and that is a much longer equation here for 9.78. All right, so 9.78 in the book has all of this in there. We can see that we can understand our y elevation based on what our initial y was plus and then a bunch of parameters based on how far downrange we are at that point, what was our initial velocity, and what was our launch angle. All right. Okay, so for case 2, reminder, that is when our coefficient of drag is based on some constant divided by our Mach number. All right. And again, we're going to have all the same kind of parameters. So here we have a parameter lowercase k2, all right, which again is based on what is our reference area and our mass of the particular projectile, the density of the air that we're in at the time. But now we're introducing this a parameter, all right, which has to do with our speed of sound in that particular medium at that time. All right. So we can then figure out our velocity. All right. Now, the Carlucci textbook prefers to use these velocities in terms of time, equation 9.86 there, that's the first one. But we also went, so you can copy this down, the McCoy version, equation 5.56 in that book, is what is the velocity based on a position of x downrange, right? So in terms of x, we have that there, all right? So whether we're looking at a range downrange x or a time since launch, we can figure out what velocity we're going to have. All right. Now, if we want to know, okay, what time am I going to be at when I'm at a certain position downrange, equation 9.88 will get you that, so we can understand our motion. And then we can look at our angle that we're coming down at, we're up at any given time. All right, our angle of fall based on our launch angle and the other parameters. And again, we can get something about our elevation as we are going downrange. All right, using equation 9.90. All right, case 3. All right, reminder, this is when our coefficient of drag is equal to some constant divided by the square root of our Mach number. All right. Again, we have a lowercase k3, all right, but now we're introducing the square root of a into there. All right, we have a square root. We can look at our velocity at whatever position we are downrange, and again, Carlucci gives it to us in terms of time, and I've given you here the McCoy version, McCoy 5.67. Which will put it in terms of position downrange. All right, so what is the velocity at a given distance versus what is the velocity at a given time after launch? All right. Now, I want to point out there is a correction in the Carlucci text, equation 9.95. All right, the denominator is squared. All right, that's not shown in the textbook, but you need that squared term there. All right, it got lost. All right, so here on the slide is a correction. Make sure you catch that and go correct your textbooks. All right. Again, we can calculate what time it will take us to get to a certain position downrange based on our launch velocities. We can calculate what angle we are at as we move in our trajectory with 9.98. And again, we have equation to get us our elevation based on our position downrange and our time downrange. All right, equation 9.99. All right, now how do we use these? This is just a whole bunch of equations. We've got them in the book to reference. What do we do with it? All right, now our first thing is we need to identify the case. What case are we in? All right, so we understand our Mach number. All right, what is the velocity that we're moving at divided by the sound speed in that medium? All right, give us a Mach number, we'll figure out our case. All right, step 2, we want to calculate the parameter of interest, which is that lowercase ki. All right, so we calculate that parameter. We end up using it in all the other equations. Then from there, we can calculate our velocity at a given distance, or to get to the distance of our target, and the time to reach those distances. All right. Given that, we can calculate our initial angle and our launch angle. All right, to give us a solution on the trajectory. All right, and again, this we have a launch angle that we initially started at, and then we have this fall angle, which is what is the angle of the trajectory as it moves through, right? So at the target, what angle is it going to come in at, all right? And once that's kind of the calculation piece of it, from that you can create a trajectory plot of your y versus your x distance, all right, to plot out that single trajectory. All right. Now, if you wanted to, the last thing you could do is to make an entire firing table. All right. So if we do this for varying ranges that we want to get to, different x's, we come up with a table of all the different, what launch angle do I need to hit the target at a certain distance, and what fall angle is it going to come in at given that particular mix of launch velocities and launch angles. All right, and that's really how we create these firing tables. Nowadays, a lot of those are inside of our computers, but traditionally those would have been even tables that you can look up in field manuals. That's kind of the backup if the computer goes down, kind of thing. But someone had to figure all that out, and this is all the math they used to do it. All right, so that's our lecture portion on our flat fire point mass trajectory, and see you in class.